Welcome, dynamic students. In this problem, we're going to use a couple of super useful characteristics of mass moment of inertia to determine the moment of inertia of a somewhat complicated body about a given point about which it's rotating. So this would be preparing us to find the I in our sum of the moments. In this case, we're going to say sum of the moments about point O up here would equal alpha, the angular acceleration of the full rigid body, times IO. And this is basically IOZ. So this is looking at the moment of inertia of this lollipop kind of shaped body, which includes a rod, and it's really a straight line, about an axis that's kind of pointing, I'm drawing a little isometric here, about a z-axis that's coming out of the plane of the screen. And this is what we'll be looking at mostly for rigid body planar motion, because this is probably going to rotate, translate, move somehow in the plane of the screen. So all of the rotation is going to have a vector, kind of our k hat is going to be pointing out of the screen. So we need to know what the moment of inertia is about the rotation axis that's pointing out of the screen. So that's, if you remember back from some of this being introduced at the end of statics, this is known as the polar moment of inertia. And if we know what the moment of inertia about the two axes in a plane, I sub x and I sub y, that I sub z is just the sum of those. But in this case, we can calculate that a little bit more directly. We're going to use the parallel axis theorem, and we're going to use, I believe, depending on what we look up, and we're definitely going to use the composites method for determining a composite moment, mass moment of inertia. So okay, we have a composite body. It is rigid, so basically this bottom plate, it's like a disc down here. We know its mass, it's 4 kilograms, and we have some dimensions. Basically, we're told it's a circular disc, and it has a diameter of 1 meter. So radius is 0.5 meters. And it's welded to a rod that has a length of 2 meters and a mass of 2 kilograms. And we need to know I total, the total body, about the z-axis through point O up here. So this is point O right up at the top of the rod. So we can use the method of composite moments of inertia. And this basically comes from the fact that if we were to look at the definition of I total, just going back to our fundamentals, we would integrate over the whole mass of the whole body. Some expression for r as a distance from O, dm, and we'd integrate over the whole body. But if m total is m rod plus m disk, then dm total equals dm rod plus dm disk. So we know that we could break our I total integral up into integrating over just the mass of the rod, distance from O to some point, dm rod. The integral of a sum is equal to the sum of the integrals. So dm disk. So this is nothing more than I rod in the z direction about 0.0, and this is nothing more than I disk in the z direction about 0.0. Now, this is where we're going to end up probably wanting to invoke the parallel axis theorem, because we can probably look up the mass moment of inertia of a disk probably about its center of mass. That's a nice handbook problem. And then we're going to need to use the parallel axis theorem to find what that would translate to about something off the center of mass. But that's we can get to that later. But that was just wanted to refresh why we can use this composite moments of inertia. It's literally flowing right back from the very definition of mass moment of inertia. So we'll just put this as a guide. We can say this is the sum of I disk z about O plus, we'll get rid of this. We're not going to use the moment of inertia yet, but we'd be ready to if we needed to solve a kinetics problem. And we have I rod about z in the z direction about 0.0. Okay, so let's start stepping through this. Let's start with what I think is the little bit more complicated one. So let's start with the plate. And let's assume maybe we didn't have our handbook with us, and we're like, doggone it, I can't remember what the mass moment of inertia is of a disk of some kind of plate about its center of mass. So we're going to assume we got uniform density, and so the center of mass is at the volumetric center. This is an area problem. We're assuming we have some kind of uniform thickness going in the z direction, so mass for uniform density is effectively equivalent to area. So it's kind of an area-based moment of inertia. Mass moment of inertia is area moment of inertia here. So if we were looking at, if we couldn't look this up, and in a lot of cases, for instance, in your Hibbler 14th edition, if you're using that book, I think there's a table of moments of inertia in the back flap. There's lots of tables on the internet, but say you are without it or can't read it for some reason. This one's easy to calculate from basic principles, and it's not bad practice. So in this case, we can say, we're going to start with the moment of inertia of that disk about its center point. So we can just again invoke I disk zc, meaning about its center of mass, is equal to the integral over the mass. The radius squared from that center point to any little mass bit there, dm. Okay, so the challenge again becomes defining the mass unit. We can say dm equals rho dv, which, given that we're in a 2D problem, is rho dA. And we can remember that the area, the differential area for a circular element is rho d theta, or excuse me, r d theta dr. So I disk cc, at its center of mass, is rho times the integral r squared dA, which is r d theta dr. So we end up with integrating from 0 to 2 pi, and then integrating from 0 to our radius, which in this case is 0.5 meters. Oops. This is something you could probably look up in a handbook, but we've got r cubed d theta dr, and that's going to end up giving us 2 pi times the density times 1/4 r to the 4th from 0 to 0.5 meters, the radius of our plate. And rewriting again, we can rearrange some terms there before I plug in those limits. Then the bottom one is 0, so we're just going to end up with the upper limit from 0 to 0.5 meters. So this rearrangement is again separating what's going to end up being the mass of the plate and then some squared distance, some squared linear term that's going to give some indication of how far that mass element is. So that's the kind of units balance that we're looking for. So in this case, we're going to end up with mass times r squared over 2. So this is something you should be able to find in a handbook. If you looked up an IZC of a disk or a circle, you should probably see something like that, m r squared over 2. And so if we plug in r as 0.5 meters, we're going to get 0.5 kilogram meters squared. Okay. So we're going to just rewrite that up here. Plus, and now I can erase all of this. So that was getting my IZ plate about its center of mass, but I need their plate disk plate, that circular thing at the bottom. I need to know what its moment of inertia is about point O, not just about its own center of mass. So here I'm going to invoke the parallel axis theorem, and I'm going to look at what is the radius from this point, the center of mass of the plate, the disk, up to point O, which is 2 meters plus the radius of the plate, the disk. So that gives me 2.5 meters. So I'm going to square that, 2.5 meters squared times the mass of the disk, which we were told is 4 kilograms. So that whole expression here is I disk about the z-axis at a point O. So if I add all of that up, I get 25.5 kilograms meters squared. Now, the rod's a little bit easier because that's something that we can look up directly in a handbook typically, the mass moment of inertia of a slender rod about its end point. And that is in fact mass times the length of the rod squared over 3. Again, we could, if we had only an expression for the rod about its center of mass, we could again use the parallel axis theorem and just move that with the r squared in this case being 1 meter, moving it over. But as we have a formula directly, again, handbook formula, where we can use an L of 2 meters. So the mass of the rod was 2 kilograms. Length is 2 meters squared. And then we're going to divide by 3. And that's going to give us 2.667 kilogram meters squared. So our I total in the basically around a z-axis going through point O is 28.167 kilograms meters squared, and that would be what we would need to know if we were going to try to relate that to, say, the sum of the moments on that rigid body. Now, another interesting way of expressing this, and this is in fact taken from the Hibbler 14th edition dynamics book, and this is problem 1710, in case you'd like to reference this. We can relate this to something, basically another way of expressing moment of inertia, and that's something called the radius of gyration, which is a real handy term, and it's lovely when somebody gives that to you. What that is effectively, it's a construct. And what it says is that this is the radius at which we would have to put all the mass in the body if it was a particle. Such that mass total, if it was placed at this radius, and rotated about the axis in question, would give the same I total as the whole rigid body. So we can literally say I total that we just calculated in the z direction about point O is equal to our gyration, the radius of gyration, let's spell that right. We'll just say r sub g, make it a little easier, squared times the mass total. So it's a little bit like the parallel axis theorem, except we put all the mass in one place, so to speak. Kind of similar there. And it uses the same properties of integrals, except in this case it takes all the mass and sticks it in one location. So very handy if somebody has already, say, calculated the mass moment of inertia, and maybe we're changing density or something. So the distribution of mass is the same, but the total changes. A uniform material change might be the only thing that did that. So all we would end up changing is the radius of gyration. So we can basically adjust our total moment of inertia with changing mass, and we're using a single number to describe the result of all of this integration of distribution of that mass about our axis of interest. Okay, so I believe the problem 1710 says, what is the radius of gyration? Well, having calculated our total moment of inertia about the point in question, in the direction in question, the z direction, and we know the mass total is 2 kilograms plus 4 kilograms is 6 kilograms. All we have to do is some simple algebra. So the radius of gyration is our I total z through point O divided by mass total square root, and in this case that gives us 2.167 meters. So if you're looking back up here at our problem, we got point O. If we were to measure down about that far, if we took all of the mass and put it right at that point, we would end up with effectively the same moment of inertia as the body that we were given with the disc and the rod. So that is a more shortcut-rich method of calculating mass moment of inertia, polar moment of inertia, in this case about the z-axis, which is the one we would be using if we were using that moment of inertia as part of our sum of the moments and angular acceleration expression for a planar kinetics problem. If we're going to move that pendulum, rotate it about some point, maybe point O. And we looked at calculating that using a combination of fundamental principles, of handbook numbers, a parallel axis theorem, combining moments of inertia of individual parts, so composite parts, and then we reviewed the definition of radius of gyration and showed how it related total mass and the total mass moment of inertia. So this type of method is probably something that you're going to use more and more often when you're solving rigid body planar motion kinetics problems. Most of the time you're going to be really concentrating on the free body diagram, on the kinematics of motion, which is where, like it or not, you're going to get a lot of the equations you'll need to solve. Moment of inertia is in a lot of cases going to be kind of the simplest part of the problem. But if you don't get it right, one of your fundamental equations of not equilibrium, equations of motion is not going to be correct. So it's very important that you calculate, you're able to calculate your moment of inertia correctly about whatever point that you're summing the moments. A lot of times it'll be the center of mass, especially if you're breaking up rotational and translational components of motion, but other times it'll be about a fixed point that's convenient. So this gave you a lot of tricks to do that so that you know your I in your sum of the moments equals I alpha is going to be correct as you go forward. So that is it for this mini lecture, and subsequent ones will deal with putting this together with other equations of acceleration and kinetics to actually solve some rigid body planar kinetics problems.